Like this, like formula they give you. It's like
You use it.
do a system equation. Well, for this one, you don't have to do a system equation. It's like
Sorry. You know,
we already knew it.
I'm not.
We have to make a logger. Yeah. One month.
Yeah.
Oh, so we got this right.
Yelling, like. And then. Combine but I can show you how to do it.
Yeah, so basically the first one, like, they kind of did it, like, they got it right, but they did it the wrong way. Because,
This is easy, you know, this
yeah,
is
because BLN was zero, so basically just A equals.
nice.
Yeah,
So you
so you don't even have to do the equations for it. And V equals, well, I didn't get it in.
You got 30 seconds.
System equation. It's like subtractive.
Didn't use it. And I got. So I know.
You know it.
Yeah, hope the best.
We play here.
I'm so convinced that we had like a. And
Like a special kind game of leader. Play like 25 games. You only have 4 on.
Sure was.
Okay, folks,
Oh.
if you haven't had a chance to finish talking about it, that's fine. Today's lecture is fairly quick. So what's going to happen today is we're going to talk a little bit about the midterm / test, then do the lecture, and then you have time to work on the new assignment. The new assignment is 2.15 from the packet. There's no more online assignment for this unit. So you'll be finishing up the packet. Shiv is happy about that. I appreciate that.
Oh, sure.
You should have you like.
And frankly, many students from my other class were able to finish it pretty quickly. So midterm, how are you supposed to study for this midterm? Connor, do you have a review packet?
Yeah.
Old review. Yeah, right. Old review. Yes.
Like look
Yeah, look over the old tests.
Yeah. Trying to
Yes.
do the problems.
That's like getting into the pocket.
Good question. Will we be getting review packets?
Hopefully.
They're available now online.
Oh.
Yes. So Connor, you were actually correct. You will get a review packet.
Oh.
I believe they do. So yeah, it wouldn't help to get other ones. It's not like more practice. And remember, packets also very often the notes from the lecture notes. We don't always get to every problem, so make sure to do some of those. Or sometimes if there are practice problems at the end of the section, do some of those. But when it comes down to it, it's up to you to know what's been important in this class, what's been emphasized, and to make sure that you're solid on that. So that's up to you. Yes, Emma?
So the midterm replace your lowest test?
It might, if you do better than your lowest test.
Okay.
So hopefully you all will do great and it will just replace whatever was not great. Yeah, Jonas? Oh, I never talked about calculators unless it's specifically a calculator test. But I am going to ask you to make sure your calculators are charged. And we'll see what happens. We'll see. Yes.
I should have, so. I don't know if you just said it already. I'm sorry. I'm like so tired. Is it worth two tests or is it probably worth on its own or?
Well, it replaces one test. And it's actually worth the same as all tests.
Oh, okay.
So I guess it's kind of worth 2 tests because if it replaces another one, that's 2 tests.
Is it in a different category? Or?
No, it's in the same category.
The question I have is, how long do we have for? Is it like an involved?
It's 60 minutes this time, so a little bit longer. Yes,
It's like
Oliver?
substantially like
If you do worse than like a test, does it have to count?
It does have to count, but it won't count for, it won't replace one of your test grades. But that's purely hypothetical, because I know that's not gonna happen. Yeah. I guess it sounded like you had to follow up
I'm
questions.
just curious, is like, since it's like 10 minutes longer, is it like substantially bigger or is it
It's about 20%. Yeah.
20% longer?
Yeah.
Oh.
Ellen, then-
It's like as the other test, or is it a little bit easier because it's more like, did you say it covers more topics?
Mm,
Would it be like,
And then for admission, they said it was gonna be like it's covering all the topics, but there is all like not like structures. He's actually do those.
I'd say we're probably hitting the same level of difficulty. Yeah, so it's about the same depth for a large amount of stuff. Nathan, did you still have a question?
Do we have the same like opportunity for the finals? Like,
Yeah.
oh, the finals.
Yeah, so final will be able to replace one score in the second semester. Two more questions, Max and then Jonas.
My question's kind of specific, but could I get my spec for like the test correction?
Yes, definitely. If you could remind me towards end of the class.
do you have the,
It's Jonas.
Is it gonna be like equal parts? Is it gonna be like, it's like this unit gonna be like kind of encapsulated with it, or is it gonna be exclusion plus a couple of them?
This unit, it will be about 50%. And then 50% will be grab bag, other stuff. So let's finish the unit, shall we? And next time there's still a review day, so things are looking good. Okay, we're gonna start on page 12. And also today we're gonna be doing the student survey.
oh, yeah,
So we're on page 12, is that what I said? Speaking of which, you like the page? Remember how to do this?
Oh, that's a.
30, 60, 90.
30. You go from the short leg to the long leg, you multiply by.
Wait.
Root 3.
That's why it answers. Well, 4 root 3 times root 3. That's why it answers 12. But anyway, let's take us back into advanced pre-calculus land, geometry land. And remember that last time that we modeled this, right? We made the scatter plot, and could you show me what the dots looked like? You just kind of trace it on the whiteboard in front of you. Kind of like this, right? Growing slowly. That's why when we did the regression, it was a logarithmic regression. And then you were able to get that nice log equation and come up with all those beautiful answers. Yes,
Ellen on the calculator though, but there's a.
there is only L.
Okay.
It seems limited, doesn't it? You like that? I'm happy it works for you. Okay, today we're just, and then one more example here. Example 3, the most common and preferred method to measure sound intensity levels is in decibels. You've heard of decibels, haven't you? Sound intensity level, beta, of a sound having intensity I in watts per meter squared is modeled by this function. Notice this function is logarithmic. Can you imagine what this function looks like?
Yeah.
Does it pass through the origin?
Yeah.
No.
Oh, does any logarithmic function pass through the origin?
0,
Some of
1.
them.
0, 1. Wait, 0, 1?
Wait, no, it might move up.
1, 0, I think. 1, 0.
Oh, wait, yeah.
But if you have a
1 plus A.
horizontal shift.
Yeah, if there's a horizontal shift, yeah. So if you tweak it a little bit, there maybe then it'll cross it. But basic logarithmics will never cross that 0, 0 unless there's a horizontal shift. It's like someone does something crazy like that. So what we're going to do is model this situation. So we're talking here about for noisy traffic, it has a sound intensity of 1 times 10 to the negative fifth, which I believe is just 10 to the negative fifth watts per meter squared, and it corresponds to 70 decibels. A loud concert has an intensity of 1 and corresponds to 120 decibels. Use the given data to write 2 equations that can be used to find the values for constants A and B in the expression for beta of I. I'll give you a moment to write those 2 equations, check with your neighbor.
Okay. Yeah, oh, it's just a simple. Oh. Okay,
Log.
no, what is it?
What did you guys?
Please.
Okay, no, you're right. Okay, 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 so. So 17 equals 1. A plus B log 10 to 1/5. Wait, no,
Well, I. Just a.
10 to or
Yeah, sure.
is that good?
Negative.
Do you get the two equations?
Yes.
I'd like to call on someone in just a moment, so make sure that you have something. Okay, Una, can you tell us the equations that you got?
Equals A plus B log of 1 times 10 to the negative 5. And 120 equals A plus B log of 1.
Are we okay with these?
Yeah.
Yeah.
Thank you. B is the 70 and 120.
No.
Wait, where's B next to the law? Like A plus B.
Oh, excuse me.
That's a
Thank
big.
you. I missed that. So is that B log?
Yeah.
Is that what you said? Sorry, Una, I missed that. And of course, nice, locked in. Log of 1, when you wrote that, you said to yourself immediately, should I just write 0? Did you think that to yourself? Yeah, let's simplify this. So this is just the same thing as 120 equals A, isn't it? And maybe in the other one, instead of 1 times, did you just write 10 to negative 5th? Did you already simplify this?
No, because it's hard to simplify.
No,
Try to
no.
simplify it. It's actually
It's
No,
1
wait,
over.
it's
Wait.
120, so just negative
1 over
50.
10.
Or 0.
It's negative 50 equals
It could be 2 or
B log.
I mean, 1 squares is 1.
So it becomes A.
A is 120.
Is 120.
They just-
I'm just rewriting the equation first. I'm not gonna-
Negative 50.
You can do negative 5. You get that part.
Are we good with that? Minus 5B? Does that make sense?
You brought the negative up.
But the negative 5 comes down and log of 10 is 1.
Oh, okay.
So it's just a little bit simpler to work with the two equations now. So find the values of A. It's like it already happened.
B is-
How should we get B?
You just
Plug
put
in
120, so.
Yeah. Can you show me what you got for B, please? Show me what you got. Yeah, you need 2 hands for this one. Unless you're showing me in sign language, you know the American Sign Language for 10? Remember?
This,
In one hand,
It's like.
oh,
this or
one,
something.
it's like,
it's shake the fist, yeah. Shake that fist. Okay, so what we have is our equation is B of I is equal to 120 plus 10 log of I, is that right? It feels wrong to write I as a variable, doesn't it?
Yeah.
There's something in me kind of,
You just
Dies.
1.
I see what you're going through, Shiv.
Yeah, should.
You okay?
Maybe Moss on the Raiders.
Yeah. Wait, what did you say?
Moss on the Raiders.
Yeah, just like, that's exactly what I was thinking.
Yes, yeah, should.
I don't watch basketball, so I'm not sure what you're talking about. Okay, so human eardrum can burst. Oh, that's a nice thought. When the sound reaches an intensity level of 1 times 10 to the fourth. Find the number of decibels required to burst a human Eardrum. Oh,
Oh,
happy Monday.
Is that real?
I think it is.
That's it.
Let me just use the equation of.
A woman in Ireland used the one.
I have this little machine.
Alright, so basically we just plug in and. The intensity. Basically log of and the.
It's so.
And it's 40. So it just.
Yeah.
No, 10 to the fourth and then log 10 to the fourth,
Yeah.
4 to the other side.
So.
It's 40. So it's just 160. Yeah. I don't even.
I mean.
It just flew out.
Yeah.
He honestly can say none. Wish I had asked him because I can't.
No,
I
but
don't
since
trust
the
my.
last quiz, I've been like, wow.
Oh, I sent.
I got 100.
And also.
Also,
We can do.
On the count of three, let me hear what you got. 1, 2, 3. Are we good with 160? Any questions?
1 a.m. 16.
Right, this whole thing becomes 40 right here. 10 times 4. So yeah, 160. So I did a little bit of searching on the internet.
Yeah.
Yeah. So yeah, concerts about 110 to 120. Fireworks are 140.
Oh,
Fireworks are 140.
140.
Oh, wow. Wait, that's so close. Wait,
The warning.
Yeah.
Wait.
Oh, dude, that's really
wait,
But-
Yeah,
that's-
yeah, what level?
right. That's a little love for you here. Your drums.
wait.
Exactly. Can't waste them. That's it. Your whole life.
That has to be right.
If you have two fireworks, is it louder?
They go off at the same time.
Is
Good
it?
question.
Would that burst in your thumb?
So very.
No, but the thing is, you have to do like right. You have to do like.
Yeah, I don't think I'm it.
It's just not as feeling. If you're far away, like the one, it's not. You don't feel the one.
I'm with.
Okay.
See, like.
Are we good with the 160? Avoid that. It's a helpful tip.
Yeah, we call it backwards.
Connie, you have a question? Oh, I'm glad you asked. We're about to go over that. But before we do, quick fun fact. Chatterbox. So decibel comes from two pieces. Of course, you know decibel refers to the number 10. So specifically, it's the fact that the level of sound found and is multiplied by 10 as part of the formula. Okay. And the bell refers to Alexander Graham Bell, the inventor of the cell phone, and the person decibels are named after, which I guess explains why it is a capital B. Kind of interesting.
Why would it be 2 L's? Oh.
What?
This guy's on some 2 L's. Who's really named after him?
Uh-huh.
Ooh.
Well, because we like to simplify. I don't know.
Snaps for that.
Yeah, you're right. It seems like it should be.
Don't you study where the origin of the name comes from?
Yes, but I can't tell you. You're too young. Okay. Yeah.
I wish something was named after you.
Oh, that's an interesting question.
Do you have kids?
No, no kids. So no one named after me. No, I don't wish anything were named after. Thank you for asking, Linda.
The sun.
The month.
Oh, but I really want to answer Connor's question though. Yeah, he had a question about semi-plots, so let's get to it. Yeah. What a coincidence! That's what we're doing today. Yeah, I agree.
Oh my God.
So we've talked about these before, haven't we? Do you remember last year when we talked about these semi-plots?
No, not here.
It's gone. It's gone.
Far away.
So here you see we have a model of a function that appears to be
Exponential.
exponential. Nice. Exponential in this case, you can see that what's happening is that this is the population of people from England in America after the year 1620, I think is what it says.
1620.
Yeah, from the year 1620 to 1820. It's so random. But you can see that that number of people grew. And it's very difficult to see what's going on here. Although it's quite easy at the other end. So, and what a semi-plot does is it scales these values down all the values down so that the smaller ones can come up and the bigger ones can come down by taking the exponential and logging it. And we'll be doing that today specifically. And the key that you need to know is if you start with an exponential function and put it on a semi-log plot, it will appear linear. I say that one more time because it's a big thing for today. If you take an exponential function and plot it on a semi-plot, an exponential function will always appear linear. So you can see the beginning of this wasn't actually exponential. This became exponential from x equals maybe 40. After that, it was exponential. There was just madness going on down here in the beginning. It's very difficult to see. But like after 60, you can see that this is, what number is that after? Like,
I would
is that
say,
100,000?
wait. Oh, yeah.
So it's difficult to see on here, isn't it? Because the first scale is 1 million. So just making it logarithmic makes it a little bit easier to see those values.
Y-axis is log.
The y-axis has been what's called logarithmically scaled. So let's do some of that. Okay, so here's another question about Mr. Passwater who made these materials. Brian Passwater is right.
Do you work here?
No, I don't know who he is or where he is. Anyway, after he tells another one of his hilarious math jokes, he begins to spread around the school. The number of people P that have heard the joke after T minutes is graphed on the semi-log plot here, where the vertical axis has been logarithmically scaled. Which of the following functions could be a model for P? Take a look at it and discuss with your neighbor.
It's exponential. Wait, exponential that looks linear?
Yeah, I agree now.
Because A,
Yeah, this is exponential.
C is long, so. it's not-
Okay, wait, ready?
Oh, yeah.
Wait, no, it's definitely B.
This is linear, isn't it?
Yeah, it's so neat. It's definitely.
Yeah, wait, is it semi-plot?
It's in B.
Yes.
This is pretty. interesting.
But like, we celebrate a little bit,
Yeah.
they did.
Yeah.
We're gonna celebrate stuff.
Oh, the next one. Yeah.
Okay. Let's use process of elimination, shall we?
I've got this.
We're ready.
Got it?
No, wait, actually.
Is it possibly A?
No.
Why not?
That is linear.
It looks linear, but we know that this is a semi-plot, and semi-plots are not quite what we're accustomed to, right? Like this is 10 to the first, 10 squared, 10 cubed. That is a semi-plot. Here we have that same thing, but don't we? 10 squared, 10 cubed. This is a semi-plot, and it appears linear, which means that relationship is exponential. So it is either B or D.
It's not B.
Obviously B.
It's D. This is
Is it D?
E.
How do you know?
Because it's exponential.
Okay, plug it
He
to.
doesn't even follow the level 4 level.
What's that, Emma?
No, it's not me.
Wait, but is it?
Wait, B follows.
And it's supposed to be.
But it follows the form, but.
Right, exponential is y equals
ABX.
a times b to the x. Isn't there only one that follows this?
Yeah, we're kind of.
Yeah, you.
I said it was easy.
Yeah,
Yes.
I agree with what you said, and that's what I thought, but I just wanna know, how do we know that that wasn't a vertical translation of two B?
When you see the linear like this, we're not dealing with any sort of vertical translations at all. It's gonna be very straightforward, a times b to the x. And aside from that, once we suspect that that's the one, did you check some points?
Yeah.
Like, what do you check?
Let me check. 0,
0, like if you plug in a 0 into d, you get
2, and
2.
3.
Does that match this?
Yeah.
Yeah.
Both
And
B.
1, 2, and yeah, let's plug in a 3. If we plug in a 3 into here, we get
That's the same thing.
16. So this is 10, this is 20. Since that's maybe 16 right there. Yes.
I'm just confused why the graph like looks like that. I'm like, why it's like gets smaller and
It's like
smaller.
a guitar. It's like a guitar.
It's like a guitar.
Okay, so between 1 and 10.
It's been logarithmically scaled.
It's like it gets smaller and smaller.
Yeah. Right, yeah, those, it's warped, basically.
Oh, pretty good.
Yeah, Max?
Well,
Okay, so on these types of problems, we won't see any vertical translations.
You will not. So far so good? Okay, important note about semiplots. When we logarithmically scale the vertical axis for a semiplot, we are not changing the actual y values of the data. And to logarithmically scale the vertical axis means that equally spaced values on the y-axis are proportional, whereas equally spaced values on the x-axis are linear. So there's no change in the x's. So the semi-log just means half of that has been logged. And if I look at the ratio here, what is the ratio of 10 to 100?
1 to 2.
It's
Whoa. Square.
Oh, 1 to 10.
1 to 10, isn't it? And 100 to 1,000. It's 1 to 10. The ratio is constant. In other words, there's a common proportion or common ratio. Okay, so example 3. Now, if you take a look at this, do you see what kind of relationship it exists?
I know.
yeah.
Is it? Is it? I'm not sure. Maybe it's arithmetic.
Neither. It's semi.
Maybe it's quadratic.
3 for 3?
I feel like
MD.
it's a logarithmic because when I see the point.
Ah.
No, it's exponential.
No, bro.
Are they?
It's like
Use that.
20, 30.
Really?
20, 30,
Input
25.
is equally spaced. Oh.
Yeah.
It's
Those are cool.
And the outputs are 2/3 of each other.
It's like exponential.
Yeah, to be exponential doesn't have to be a common
Multiply.
Ratio.
common
It's a
multiple,
ratio.
a common ratio.
Which
Is there a common ratio?
Damn it.
There's a common ratio.
2/3.
One sushi, you talking.
No. 3 halves.
Three halves.
Go to school?
This divided by this,
Yeah.
isn't that 3 halves? And this divided by this,
3 halves.
3 halves.
It's kind of tricky.
Is also 3 halves, but yeah, so the next one should be 202.5. To be perfectly exponential. So we've established that it's exponential. The question is, which of these models
The linear
the
one.
function?
Yeah. But then I wouldn't get to.
You sure?
Yeah.
I mean, that's. what
Because
you said.
exponential looks linear on
I
a
would hope
semicolon.
so.
It's definitely.
Half of the best.
We've been good.
It's not.
No, I'm using A and B constant. A and B, A and B in an exponential function.
Well, we are
So I
the
I heard it.
here.
we are the root x.
Okay, so you see, there's only one obvious answer here. It is D. What's wrong with C?
It's so close, but so far.
Yeah.
That's be proportional.
It would work if it was like
150 to 100 is not the same as 100 to 150. This is a normal scale, isn't it?
Yeah.
It's a normal scale. Yes.
Will we ever see a semi-log plot that's not like log base 10?
Probably not, but there's a chance in life. But I think in this class, it's always going to be based in. Okay. Here's some practice for you. I think we've done some similar to this before. Let's see if you still got it.
this is really bad.
Wait, so this is 200?
Yeah.
And then it goes 300?
Like this is might be the easiest.
Yes.
Well,
If only had time.
I'm just guessing.
200,
Wait,
25.
25 is in between one right here.
Huh? Yeah.
Wait, I understand.
Yeah. Alright.
Race.
whoa.
Right, next one.
2 comes up. You're done?
Yeah.
2 to 7. Oh, I know. 2, 3, 4, 5, 6.
I thought it was a T.
Alright,
0.2.
let's go to this next problem. Sine plot well corresponds with data table, for example. Example 3,
Are we doing?
it's like a whole different page.
Here's just example 4. Just doing this one.
Oh, just 4.
Oh, just 4?
0, 200.
Are we done with the 5 points? Okay, let's do it like we did last time. Let's just tell me when to stop, like 0, 200. And then go up this axis and then tell me when to stop. Tell me when to stop.
Right there.
Are we good right here? Is that 0, 200?
Pretty much.
Okay.
Oh, low.
Okay.
Yeah, I got my. Into my bag. We have the same. Oops, I did it again.
I think we're
Yeah. Yeah, this is great. You think, okay, well, let's see. We're gonna try this again. 125. We're gonna start down here at the bottom and then animate it. So just tell when to stop.
Oh, we're getting close.
Right there?
now.
Oh.
Right there?
Save.
Right there.
Right in the middle? Should it be right in the middle?
Yeah.
Remember, yeah, a little bit of brown.
Yeah.
Because everything's squashed at the top.
Math just makes sense.
It's weird.
Wow.
Sometimes it makes sense, sometimes it makes people crazy. Okay, 2,7. Okay, you sure you're ready? You're strapped in? Okay. Helmet on? Here we go. What is this right here?
6, 7.
Oh.
All right there? Is that right? 2, 7. Does that fit with 10? Did it go up to 10? Okay. 8, 9, 10. That's perfect. Oh, thank you. 3.2 is X wonky at all?
To the right a little bit.
I'm just gonna move to like right here, right?
Yeah, that's exactly where.
Uh-oh, my animation didn't work. Okay. Okay, so 3.2. Oh, I lost it again. Okay, so I'm just gonna go up there. Want to stop, please? It is hard to see. That is hard to see. Oh no. Right about there? Oh no. I messed up, didn't I? Oh, thanks. Like right there?
There.
Yeah, I figured that's where you're going. Thank you. I appreciate that. Then 4.6, comma 1.5.
Third dash.
The third dash, exactly. Then we go.
Yo, this is really hot.
Stop.
No,
Did I go too far?
Right there.
like a little bit more than midway.
A little bit more than midway. A little bit more than. And I think the best way maybe to think about that is like where is that 50? Like, where's 50 in here? It's not halfway, right? It's all skewed up a little bit. So same kind of things happening in between. There's scaling all over the place. So far, so good. Okay. So what we have here, and there's a little bit of room here for notes. We're taking exponential functions and we are logarithmically scaling it, which means I'm just going to take the ln of both sides. Well, not ln, I'm going to take the log base n of y equals log base n of a times b to the x. What can I do with that right side?
The distribution.
I can make an addition, can't I?
Yeah.
Right, it's a product. So we have log base n of a plus log base n of b to the x. Can I do anything else with this? We could take the x and yeah, and I'm gonna write it like this. I'm gonna say log base n of b times x plus log base n of a.
You could also go like that.
Yeah, I'm kind of forcing things. I'm kind of forcing things because I want to point out that this is what kind of a form. It's linear, isn't it? Y equals mx plus b. Right, so the exponential, when we scale it logarithmically, it becomes, and not by coincidence, it becomes linear by just the relationship of these values. And we still have log base n of y equals that. Yes? Okay, there are two notes along with this. First of all, there is a little bit of an error in the linear model. Instead of y, that should be log base n of y. And I think what they meant to say was that this is linear. So I'm going to put a big Y on there just to hopefully not confuse it. There's original Y's and there's a scaled Y value. Yes.
So does this linear thing take us back to the original exponential graph?
Yeah, we could go back and forth.
Oh, okay.
Exactly. So this is showing a relationship. And remember what A represents? Its initial value, and B represents the growth factor, otherwise known as the
Rise run.
common ratio. So A is still, what do we call it? A is the initial value. And B is called the growth factor. I think that makes more sense with exponential. The slope of our linear function is log base n of b, and the y-intercept is log base n of a. Does that make sense? Note number 1. And that's what we got when we took the ln of both, the log base n of both sides. And note 2 is very important, and this gets to the question that was asked earlier. Base n corresponds to the base used for the scaling of the vertical axis. Right, so Haley, you had asked, is it always 10? In our class, it'll always be 10, but it doesn't have to be. It could be anything. Yes, Connor.
So is b the slope or is log n of b the slope?
Log base n of b is the slope. Yes, sir.
Can you determine which part is like the rise and which part is the run?
Well, rise is always the vertical.
Yeah.
Run is always the y.
What is it?
What's that? Well, let's talk about it specifically with this case. This is, I believe this is exactly the points that we've done. This is 1 comma, what is that?
It's like
1 comma 40. And this one is 2 comma 60. Isn't that the first chart that we had? It's just that again. I think that we've seen this graph exactly. So this was 1 comma 40. This is 2 comma 60. This was 3 comma 90. So if you try to find the slope of this, it's a little bit weird because it doesn't rise the same every time, does it?
No.
Is that right? Well, it's been logarithmically scaled. This is an exponential function that's been logarithmically scaled. So it looks linear. But let's talk about the slope here. The slope is equal to y1 minus y2 over x2 minus x1, except we have to remember that for the y's, we have to take the log of both of those.
Wait.
Oh, thank you. It should be 2 and 1 for both of them. Thank you for paying attention. Y2 minus y1 over x2 minus x1. So I could just take this 60 minus 40 over 2 minus 1, which gives me my, is this right? It gives us 20. Something strange.
We have to take the log.
Oh, thank you. We have to take the log of both of them. Yeah, I'm finding thank you. I knew something was screwy there. How can we rewrite log of 16 minus log of 40?
63 over log of 10. 60.
Log of 3 halves, right? Would we get the same thing if we chose another 2 points? It'd be the exact same thing because we're taking the logs of both. Yeah, Emma? Because we have to keep in mind that this is logarithmic scale, so we're taking the log of both y values. Yes.
The reason why the denominator doesn't have logs is because the x doesn't change.
X's do not change. Good. Exactly. Yeah, this is semi-plus, so only the y's have been messed with. Yes,
So then, like, if we have a different scale factor, like, let's say it's 5 to 0 and stuff like that, would it be like log base 5? Okay.
yes, it would. Yeah, this 10 means we're taking log base 10. We're doing common logs. Another question? Connor?
Good slope. How do you know the log?
So like if these were reversed, these first 2 points were reversed.
Yeah.
Log of 40 minus log of 60. We log of, instead of log of 3/2, we log of 2/3.
Wait, that's
I get it.
2/3 would make it right.
And it does, yeah.
So it's like the
Between 0 and 1.
Okay, so we have, and this should be log, it should be log of y equals log of 3/2 x plus log base n of a, oh, log of a. Yeah, how do we get log of a? Oh, do we know a?
we could just put, wait, but we don't have
Is
it.
it 40 the initial values?
Do we know the initial value?
Figure it out.
You can figure it out, right? You could go back to here. I think you could go back to here and just figure out the initial value. What do you?
Didn't always want.
No, it's
If it hasn't been stretched, but with that a, remember, as y equals a to the times b to the x, it's always going to be a.
3/2.
So let's follow this through with this, and then I'll show you that that's kind of a waste of time. So to figure out a, I'm just going to plug in any point. Which point should I plug in?
140.
I'm plugging 1, 40. So log of 40 equals, oh, so that's like a 1 in there. Oh, that's nice. Plus log of a, log of 40 minus log of 3/2 equals log of a. What is log of 40 minus log of 3/2? It's 80/3. Nice. So there it is. There's my log of a. So this is our log of a.
Is the log included or is a?
It is included.
Log?
Oh, I'm sorry.
Is
This equals log of a.
okay.
So log of a is, in other words, a is
80/3.
80/3. So my final answer, log of y is equal to log of 3/2 x plus log of 80/3.
Could also just said like 3/2 x equals 40.
Yeah, that's probably what I would have done because this is weird.
Yeah.
It's gotten really strange. So let's take a look at B using the linear model from part A. And what makes this linear?
Oh, the fact like I mean,
The y.
That's mx plus b.
Okay.
Makes it linear. So it looks linear, but remember, we know that it's actually exponential. So rather than go from here, but I think that's fine. You're never going to have to go from here. Let's write an exponential equation in the form y equals 8 times b to the x, just based on what we know. Right, we already know that b is equal to 3/2 to the x. Now I just need to figure out a. How should I figure out a?
we have it already.
We did already figure it out, but if I want to start over again, I'm going to plug in the point 1, 40. So 40 equals a times 3/2 to the first power. Now we can see from here, a equals 80/3, which I think is so much more intuitive, personally. Yes, Simran?
Growth factor is the same as the slope in this type of problem.
The growth factor is the same as the log of the growth factor is the same as the slope. The log, yeah, the log of the.
Because if you just subtract the points from.
Yes. So we get y equals 80/3 times 3/2 to the x power. So that is the exponential function here. Elle, you have a question? And we already had the pieces. I think that we kind of already had the pieces. We could have gotten those pieces earlier. Like that 83rds. Do you see how you could have gotten that here? And just like what you were saying, it's just like
If you just like divide.
x times 3/2 equals 40, right? What's that, Jonas? Or were you saying the same thing? Yeah, so you're multiplying both sides by 2/3 to get that initial value. So that was a lot to take in. Take a moment to discuss these and then to get started on the assignment.
Wait, what's the assignment? 215.
2.1. So they were- I think I get them to get started online.
Just got you. Oh, I think it's
That they
concept.
get it.
Oh, I love.
Ready? 1, 2, 3, 4, 5, boom. That was on page 4, right?
Yeah, I'm gonna try to. You can turn.